Dear conference participants, I would like to present the research with the title Determination of the thermal stress state for the composite brake pad of a wagon at operational loads. The rapid development of the rail industry is accompanied by an increase of the train speed and the axle load. The need to improve the structures and materials for the rail vehicles, increase in the tare-load ratio of rail vehicles, and so on. In this regard, friction materials used in the rail industry, in particular for braking system, should provide a fixed friction coefficient and low wear at various operational and environmental conditions like speed, temperature, pressure, noise, extreme weather, and so on. The violation of the operational requirements causes an increased wear of brake pads, and therefore in operation brake pads can be used for braking. This certainly leads to damage of the rolling surfaces of the wheels and directly affects the train traffic safety. Therefore, in order to prevent abnormal wears of brake pads, including dual wedged shaped wear, it is advisable to develop requirements and devices that will ensure the uniform wear of brake pads so that they can serve during the whole repair-to-repair period at depots. This makes it possible to dispose of such brake pads with a mirror portion of the working composite mass remaining, and a lot of costs during operational and maintenance requiring railways or industrial enterprises with their own freight rail vehicles, so that they will purchase brake pads and significantly reduce operational costs. Currently, the entire fleet of rail wagons is equipped with devices for uniform wear of brake pads, but they have very low reliability. Because of this, their efficiency is lost even in those wagons that are just being put into operational from wagon building or repair enterprises. Therefore, it can be seen from the histogram that more than 90% of rail wagons work with wedge dual wear of brake pads, and almost 5% have brake pad cracks behind the temperature notch. Because of this, the braking efficiency of freight trains is deteriorated. The objective of the research was to determine the thermal stress state of the composite brake pad used for a wagon at operational loads. To achieve this objective, the following tasks were set: to investigate the thermal stress state of the composite brake pad with the rated parameters, and to investigate the thermal stress state of the composite brake pad with dual wedge-shaped wear. The thermal stress state of the brake pad at operational load modes was determined using the strength calculation. It was carried out with the finite element method in SolidWorks software. Composite brake pad 2TP11 was chosen as the prototype. The main characteristics of the pad are given in Table 1. The spatial model of the pad was built in SolidWorks software, as we can see in figure left. The finite element model of the pad was built with spatial isoparametric tetrahedrons with 4 Jacobian points. The optimal number of elements of the model was determined by the graphoanalytic method. The measure was based on the curvature. The number of elements was over 2,800 and number of nodes was over 12,200. The model was fixed by the back plate in the area adjacent to the shoe. The material of the pad was composite with linear elastic orthotropic properties. At the same time, the compressive strength of the material was taken equal to 15 megapascals and the tensile strength was taken close to 0. The design diagram of the pad is shown in the figure left. It included the horizontal load PH to the working part of the pad, the volume of which was taken according to the operational mode of the air distributor, 41.69 freight mode, 34.34 medium mode, and 17.5 for empty mode. It should be noted that the pet suffered temperature load during braking. The temperature on the rolling surface of the impeller can be determined by the analytical expression given on. By analyzing the dependencies 1, 2, 4, we can conclude that the temperature on the pet surface was constantly changing by braking time. Therefore, when calculating the strength of the pet, the maximum available value of the temperature load PT was taken into account. This load was applied to the working surface of the pet and was taken equal to 400 degrees Celsius degrees. Since the material mentioned had a small tensile strength and no yield strength, the strength calculation was made according to more Coulomb criterion. It means the theory of internal friction. It is known that this criterion predicts failures when the simultaneous action of the maximum principal tensile stress and the minimum principal compression stress exceeds the appropriate stress limits. In on slides 7 and 8 are shown results of the calculations. The figure left shows the first principal stress that occurs in the block, and the second and third principal stresses are shown in this slide. The analysis of achieved results allows to conclude that the maximum stresses occur in the upper part of the pet in the area of interaction of the backrests with the sidewall, and the value was of 14.9 megapascals, which does not exceed the permissible value of 15 megapascals. The work also carried research into the thermal stress state of the composite brake pet with a dual wedge shaped weir. The strength of the brake pad was calculated and its dual wedge shaped weir was taken into account. The calculation was made for the composite brake pad with a dual wedge shaped weir used for the wagon with a mileage of 63,400 kilometers. According to the measurements, the pad had the following abnormal wear characteristics: thickness at the upper end of 10 millimeters, thickness along the borderline of the plates 27 millimeters, and thickness at the bottom end of 20 millimeters, and length of harmful abrasion at the top of the pad of 85 millimeters. We can see this in this figure. The mass of the composite brake pad with wear was 1.98 kilograms. It was determined using the SolidWorks simulation calculation program. The resulting mass was 39% lower than the mass of a typical pad with the rated dimensions. Figure left shows the calculation diagram of the pad with wear, as well as, on the right side, the diagram of temperature load application. When drawing up the calculation scheme of the pads, the identical loads for the pads with nominal values were taken into account. The finite element model of the brake pad with wear consists of 5,429 elements and 24,502 nodes. The maximum element size of the mesh was 12 millimeters, and the minimal element size was 2.3 millimeters. The results of calculations are shown on slides 11 and 12. Here you can see results of the pad from the simulation analysis. Figure right depicts that the maximum stresses occurred in the back of the brake pad, and the value is of 80.7 megapascals, which exceeds the permissible value of 19.8%. This graph shows the stress distribution along the edge of the upper part of the brake pad. At the same time, stresses on the graph are represented by the module. To determine their numerical values, the probing option in simulation software was used. From this graph, it can be concluded that the maximum stresses occurred at the height of 135 to 140 millimeters from the top of the pet. I would conclude that the maximum stress distribution in the pet can be explained by the fact that the frictional force is taken as upward calculation. The maximum stresses occur in the back plate of the pet with the volume of 18.7 megapascals, and other findings are concluded in this text. Thank you for your attention.